Okay, here is another example. I'm going to explain that in a minute. So here we have a coil inductor. Okay, he gave us the diameter of this inductor as 2 centimeter. Okay, so if you look at the side view of this inductor, that's the diameter of that inductor. Inductor is nothing but solenoid in this case. And he also gave us the given data. The solenoid is 8 centimeter long. Okay, and n equal to 120 turns. It has n number of turns. That number of turns are 120. That's also in the given data. Okay, now this inductor is carrying a current which is indicated in the graph format. It's a time in second. So this is 0.01 second, 0.02 second. Okay, it is changing from 0.5 to negative 0.5 in 0.02 seconds. This is the graph for the current passing through that inductor. Now the question he asked, assume that there is another small ring placed inside of this inductor. That small ring is 1 centimeter diameter. Okay, and it has resistance R of 0.5 ohm. Okay, so the question he's asking about, what is the current passing through that loop, and he's also asking about the direction of the current. So the loop I'm talking about, this ring. Okay, this is the loop or ring. Okay, now first we'll find what is the magnetic field produced by this solenoid inductor. That value is B equal to mu naught Ni over L. Okay, now that current is not constant, so it is going to change, right? So can I say that B dB by dt is nothing but mu naught N over L, which is di by dt. Okay, we have everything in this equation. Mu naught is 4 pi times 10 to the power of minus 7. N is 120. Length is 8 centimeter. 8 times 10 to the power of minus 12 minus 2. Now di by dt, what is the rate of change of current? Okay, current is changing how much? 0.5 to negative 0.5. That's 1 ampere in how many seconds? In 0.02 seconds. Okay, so can I say this di by dt equal to 50 ampere per second? Okay, di by dt equal to 50 ampere per second. So if I substitute that here, 50 ampere per second, I will end up with dB by dt. Okay, now the current is decreasing, so the magnetic field inside of this coil is also decreasing, not increasing. It is changing from maximum to minimum. So this value is 942.4 times 10 to the power of minus 4 Tesla per second. Okay, that's dB by dt. Now first we need to find what is the induced EMF across the ring in that small loop. Okay, induced EMF E equal to d phi by dt, okay, where phi is nothing but BA cos theta. So here theta is 0 degrees, so I would say this value is 1, so this is 5. Okay, area is area of the inner loop. This is area of the ring, because we want to find the induced EMF inside that small ring, so I need the area of that small ring. Area equal to, that's pi r square, we have, or pi d square by 4, but anyway we can find r, which is pi times 0.5 times 10 to the power of minus 2 whole square. That value is 0.785 times 10 to the power of minus 4. Okay, that's meter square. So now this area is constant. Can I write this E equal to area times dB by dt? I already have that dB by dt right there. So if I substitute here 0.785 times 10 to the power of minus 4 times dB by dt is 942.4 times 10 to the power of minus 4. Okay, that will give you the induced EMF. Okay, so the induced EMF is 7.4 microvolt. And now the question he's asking about, what is the current flowing inside this ring? So current equal to I equal to E over R. E is 7.4 micro, R is 0.5. That value is, can I say it's 15 micro ampere. That's the current passing through that ring. Now we need to find the direction of the current direction in that ring. Now we're going to find the direction of the current inside that ring. Now if you look at the inductor, say here is the inductor, assume that the current is going in this direction. Now what is happening in this current? This current is changing 50 ampere per second, so the direction is going to change within 1 second, from one direction to other. So if current is going in this direction, assume that this is the magnetic field direction. Okay, so that's the magnetic field. Now this magnetic field, what happened to this magnetic field? It is going to come down. I mean, it's reducing. Okay, so according to the Faraday's law or Lenz's law, according to the Lenz's law, inside this ring, here we have the ring. What happens to this ring? This ring opposes that decrease in the magnetic field. Okay, so what happens? This ring is also going to produce magnetic field going in this direction. Okay, so if you hold that ring in your hand, which direction the current is passing through it? So I mean, by using the right hand rule, thumb indicates the current direction and folding fingers indicates the magnetic field direction. So if you look at here, I mean, hold it in your right hand, this red ring, okay, and see which direction the current has to flow to produce that magnetic field. So if you look at it, thumb indicates the current direction. So if I look at it, current has to go in this direction, in the clockwise direction, to produce the magnetic field in that direction. Okay, so now what if my current is, instead of decreasing, increasing? So if the current graph is something like this, okay, then the current produced in this ring is going to be opposite direction. Okay, thank you.